Swayam Prabha. Digital India. Educated India.
Welcome to the DTH sponsored course on micromachining. Today we are going to talk about micro nano abrasive finishing technologies and overview. Already done in earlier lectures. This is what we are going to discuss. Now before that, glimpses of the work done at IIT Kanpur on nano finishing technologies, acknowledgement, related books of the speaker. What we have done: micromachining, advanced abrasive micromachining finishing processes, magnetic abrasive finishing, abrasive flow machining or abrasive flow finishing, magnetorheological finishing. In this lecture, we are going to discuss magnetorheological abrasive flow finishing, rotary magnetorheological abrasive flow finishing, magnetic float polishing, electrolytic in-process dressing, that is ELID, chemomechanical polishing, that is known as CMP, and magnetorheological abrasive flow finishing, that I have already written over here, so it is just repeated. Chemomechanical magnetorheological abrasive flow finishing, and then the conclusion. Now this is the book which may be having some interesting things useful for this particular work, and most of the work or most of the things that I am going to discuss today, they are given in this particular book on nano finishing science and technology, published by CRC Press, US in New York. And some part you can get in this book also, micro manufacturing processes, again published by CRC Press, New York. And this is the latest book which has come in the market in the year 2022 September. Acknowledgement, I am not going to repeat, I will just go fast. I have already told you in the earlier lectures also. All those who have contributed to nano finishing research work at IIT Kanpur: Dr. R.K. Jain, Dr. Sunil Jha from IIT Delhi, Dr. Vijay Gorana, Dr. D.K. Singh, Dr. S.C. Jaiswal, Dr. Manas Das, Dr. Ravi Shankar from Guwahati, Dr. Ajay M. Sitwara, he is at IIT Kharagpur, Dr. Prabhat Ranjan from BARC, Bombay, Mr. Pawan Basera from HL Nasik, Mr. Satish Kumar from IIT Kanpur, Mr. Mithun Sarkar, and finally these are the projects which have sponsored the nano finishing work at IIT Kanpur, that BARC Trombay, DST New Delhi, ARDB Bangalore, CSIR New Delhi. And sorry for repetition of some slides in this lecture may be there, because I had discussed some of the things in the introductory lectures of this particular course. Magnetorheological abrasive flow finishing, abbreviated as MRAFF. Problems associated with MRF, magnetorheological finishing process, are as follows. There are shape limitations. A small finishing spot is there in MRF process, and standard magnetorheological polishing fluid ineffective for polishing hard metals, because here a small finishing spot is there, so the efficiency or the time taken is very large and efficiency is poor of this MRF process. The solution is magnetorheological abrasive flow finishing, because I have not mentioned here, there are certain limitations with the abrasive flow finishing process also. So MRF is the combination of MRF plus AFF. So we have tried to limit the constraints of these two processes and take the advantage of merits of these two processes, MRF and AFF. And this process was introduced first time across the globe by Dr. Sunil Jha, who is working at IIT Delhi. Now you can see here MRF, not suitable for hard materials, extremely externally non-controllable abrasive flow machining or abrasive flow finishing process. By combining these two processes, the MRF process was developed, that is magnetorheological abrasive flow finishing process. The viscosity of abrasive medium in MRF can be manipulated and controlled in real time, hence helps in deterministically and selectively abrading the workpiece surface. This is very important advantage, that you can control it in real time. The use of machining setup is similar to AFM, abrasive flow machining, will remove shape limitation on the workpiece surface to be finished, because AFM process is used for highly complicated and many times non-accessible areas also. So that setup is used, and medium used is that of MRF process. So we are combining the merits of both these processes, and we developed what is known as MRF process. Working of MRF process, you can see here modeling of chain structures. Here there is no magnetic field, so you can see here these are the abrasive particles, and these small particles are of iron particle or CFP particle, say carbonyl iron particles. Now you can see the setup over here carefully. This is the north pole, this is the south pole. You have the abrasive particles. Motion is given to the fluid. Viscoelastic fluid is up and down, as you can see here by the arrows, and here is the workpiece, which is this is the workpiece over here, this is the workpiece fixture, this is the workpiece over here shown in green color, and then you have the electromagnet, north pole, south pole of the electromagnet, and this is the microscopic view of MRF process. Here now you can see north and south pole are used, so magnetic field is there, but this picture shows random distribution of abrasive particles as well as carbonyl iron particles, CIP particle or iron particle, and here is the absence of magnetic field. But if you apply the magnetic field, you can clearly see the difference between this picture and this picture. All iron particles or CIP particles, they have been arranged in a line along the magnetic field, along the lines of magnetic field, and in between them or within them, these are the abrasive particles. Deliberately we have taken much larger abrasive particles just to show the picture, but in real life, in real work finishing process, these abrasive particles are of very small size, maybe micro or even nano size abrasive particles. MRF of silicon nitride surface characteristics. This is one of the result obtained by magnetorheological abrasive flow finishing process of silicon nitride. You can see here the initial RA is 0.28 micron. These are the other ways of measuring the surface roughness, and you can see how rough is the surface. This is the SEM picture, and this is the line draw showing the roughness on the surface. And after 2000 cycles with silicon carbide, you can see the surface finish has come from 0.28 micrometer to 0.10 micrometer. And but here abrasive particles are silicon carbide. When we are using diamond as the abrasive particle, surface finish obtained is here also is 0.1 micrometer, but you can see the difference in the surface texture while machining with silicon carbide and while machining with diamond abrasive particles. So it clearly indicates that surface texture is also a function of the type of the abrasive particle you are using for finishing purposes. Then there is another version of this MRAF process, that is known as rotary magnetorheological abrasive flow finishing process. Problems associated with MRAF process are difficult to provide uniform magnetic field in the finishing zone due to fixed coils at two diametrically opposite sides of the cylindrical workpiece, which is fixed. Here electromagnet is being used, that's why you can see here fixed coils are there. You can use permanent magnets also under certain conditions, and you get, in this particular case of MRAF, you get non-uniform finishing of cylindrical workpiece at different points across the diameter and length of the workpiece. So what is the solution? The solution was proposed as rotary magnetorheological abrasive flow finishing process. Our MRAF experimental setup is shown over here. It is the same as shown in the earlier case, except that you are able to rotate this electrode. This is the permanent magnet or electromagnet, this is the magnetic fixture, and workpiece is there inside this. So if you are rotating this magnet, then magnetic field is rotating and you will get the uniform finishing on the workpiece surface. You can see a VFD, variable feed drive is there, power supply is there to BFT, AC motor is here, bottom MRPF cylinder is there and top cylinder is there, another bottom hydraulic cylinder is there and top hydraulic cylinder is there, and fluid is moving up and down, that we have already seen. You can see here these are the different parts, they are used over here. I need not to go into many details, except that pictorial views of the same are shown over here. Magnets configuration in our MRAF process. You can see here, now the question is how to place the magnets. Now here you can see different ways of placing the magnet and how the flux is generated. This is the north pole, this is the north pole. So you have two north poles opposite to each other and two south poles opposite to each other, and you can get very uniform flux, magnetic flux, and these are the iron particles which are indicating the lines of magnetic field. If you place north pole and south pole opposite to each other and south pole and north pole here, then you can see this flux is centered in certain areas. Here there is no flux or hardly any, very small flux is there. So here in this case you will not get uniform good surface finish. Same is true if you are using two poles only in place of four, then south and north, and then again you have the non-uniform magnetic field over here also. So this is the MR polishing fluid over here, south pole, north pole, where you are getting the best surface finish or best uniform distribution over here as shown over there. And these are the magnetic field vector, and here you can see, compare this one with this one, you get the magnetic field in here and here only, and this is the MR polishing fluid. Here you can use the permanent magnets just like shown over there also. Only thing is here you will not get the uniform finishing. Now can you use this for knee joint problem solving? We will discuss it. Mechanism of RMRAP process. You can see over here, this is the flat workpiece over here, flat workpiece over here, here as well as here, and here are the magnetic cluster, cylindrical fixture is there, then magnetic lines of force will be in this direction, and these are the south pole, north pole, north pole. You are providing the rotation to the magnet is provided like this. So this is RMRAP process because rotation of the magnets is there, and this is how you get the helical finishing path of polishing when magnets are rotating, and if you are giving up and down motion to the fluid, viscoelastic fluid having the abrasive particles. Then you can see here, these are the abrasive particles over here. Helical motion of the abrasive particle is there, and they are finishing the workpiece, because this black line represents the workpiece over here. So you can see up and down motion and rotary motion both. Advantages of RMRAP process. It is indentation on the abrasive grain is due to combined effect of normal component of magnetic force and centrifugal force due to medium rotation, because medium is rotating over here and magnetic force is there which is pushing this abrasive particle inside the workpiece. Due to medium rotation and reciprocation, the cutting force is the resultant of tangential cutting force and axial cutting force. Path followed by the active abrasive grains on the work surface is non-linear, that is helical. Now you can see here, these abrasive particles which are in contact with the workpiece, they are known as active abrasive grains, and other particles which may be at the center or away from the workpiece surface, there may be abrasive particles here, here. They are the non-active because they are not in contact with the workpiece surface and they are not going to remove the material from the workpiece surface. It provides higher finishing rate as compared to MRAP process, because it is abrasive particles are reciprocating as well as rotating. So larger contact area of one individual abrasive particle with the workpiece surface is there. Then uniformly finishes the workpieces like honing process, and it generates H pattern which helps in oil retention. Forces and velocity components acting on abrasive particle. I will just show you quickly, I will not go into details, otherwise it will take lot of time. So these are the abrasive particles you can see over here, north pole, south pole, and this is the irregularity on the workpiece surface. So when you are applying the force in this direction, this is the force responsible for penetration, and this is the force responsible for shearing, and as a result of that, shearing takes place and micro nano chips are separated out from the workpiece and they mix up in the medium and they go out along with the medium. This is the medium up and down motion, and this is the rotation of the medium. This is the MRAP process where no rotation is provided. This is the RMRAP process where rotation is being provided. So you can see the additional forces are acting due to the rotation. Now here there is FM and MR, here FR, FMN and F centrifugal force is there. Same way, this is the resultant force, this is the resultant force over here, and you have the FT, tangential force is acting, and the cutting force is. So different forces are acting, and because of rotation, additional forces are acting which help in enhancing the performance of the RMRAP process as compared to MRAP process. Now there are certain forces. Magnetic force is given over here. This is the radial force K into P. Centrifugal force is given over there, and friction force is also given over there. So cutting force is represented by this. Comparison of magnetic field intensity. This is the RPM of the magnet or the magnet's rotational speed, and this is the change in RA value. As the rotational speed is increasing, to some extent in this particular case, first initially it is increasing, then it starts decreasing. Same is true with other two cases also, that is in case of stainless steel as well as brass, and this is for EN8 steel. So you can see here that there is certain maximum value is attained as long as surface roughness value is concerned, and then it starts decreasing, and we want the maximum change in RA value, that is, this is the change, not RA value, this is the change in RA value. So, there is an optimum where you get the maximum change in the surface roughness value, beyond which again it starts decreasing. Effect of rotational speed of the magnet on delta RA, that is the change in surface roughness value for brass, stainless steel and EN8 workpieces. Now, these are the stainless steel non-magnetic workpieces are there, magnetorheological polishing fluid etc. are given over there, and this is for EN8, and you can see here generation of higher magnetic field at the vicinity of the workpiece, that you can see concentration of the magnetic field over here, here, here as well as here. Magnetic field plot using NSoft Maxwell software with MR fluid. It depends on the magnetic properties of the workpiece material also. Mechanism of RMRAP process. RMRAP process, you can see over here, this is the knee joint finishing using RMRAP process, north pole, south pole. This is the knee joint fixture. You have the permanent magnets, abrasive particles are there, carbonyl iron particles are here, these are this little bit blackish, and lighter one are the abrasive particles, and when you are moving this up and down and rotating it, it is able to finish this knee joint efficiently. Normally, orthopedic surgeons recommend about 100 nanometer as the surface roughness value of the knee implants, but at IIT K we were able to achieve as good as 29 nanometer surface roughness value. We can achieve it even lower than this. One has to optimize the parameters. So, this is the force analysis, this is the abrasive particle, and which will penetrate over here and move so that it shears off the peaks on the workpiece surface, that is this workpiece surface knee joint, and you can get very good surface finish. Experimental results, you can see the surface roughness plot over here, very rough surface. Initial roughness of the workpiece, RA value is equal to 1.21 micrometer, which is quite large, RQ 1.52 and RZ 8 micrometer. I need not to explain RQ and RZ, these are the different ways of expressing and measuring the surface roughness, but most of the time we need RA value, so I am emphasizing on RA value only. And this is the one, RA value has come down to 0.01, from 1.21 micrometer it has come down to 0.01 micrometer, which is substantial reduction in the RA value or high improvement in the surface finish of the workpiece. You can see here, this is the initial surface and this is the polished surface with butter waste magnetorheological polishing fluid. MRP means magnetorheological polishing fluid. So, you can clearly see the difference between these two, and this is also clear from 1.21 initial surface roughness and 0.01 final surface roughness. AFM images of the surface modifying process by RMRAP process, initial ground surface without finishing, without rotation of the magnet, and surface generated by RMRAP process at 60 rpm. So, you can see here, this is the A, this is the initial surface, and B after MRAP without rotation, that is only MRAP process is used, and you can see at certain places non-uniformity is there and some irregularity, some valleys are there left over there. And if you compare this surface with this surface, this is with rotation at 60 rpm. So, you can see this is better than this. So, it indicates that RMRAP gives improvement over the surface texture as well as surface finish of the finished component. This is another example, ground workpiece is here. You can see the surface roughness peaks over here. This is the 2D plot over here, and this is the after MRAP without rotation. RA value come down to 0.17 micrometer. That is what you can see over here. Roughness peaks are shown over here. And after RM rev with rotation to 60 rpm, the surface roughness value has come down to 0.05 micrometer, and you can clearly see the difference in the surface texture also between this and this and this and this. Improvement in surface finish of stainless steel pipe by rotational magnetorheological abrasive flow finishing process. You can clearly see surface finish before finishing. Now there is no reflection of IITK on this workpiece, and this is unfinished, and RA value is 330 nanometer, although it is quite good, but reflection is not there. And this is the SEM plot, scanning electron microscope plot, 3D plot of this particular surface, and you can clearly see the peaks and valleys, and this is the 2D plot, 330 nanometer. After finishing, the surface roughness from 330 nanometer has come down to 16 nanometer, and you can clearly see the reflection of IITK letter into this finished pipe, part of the pipe which has been cut, and you can clearly see the reflection of this, the reflection of letters IITK over here, but here there is no reflection because it is unfinished. Internal workpiece surface after parting off, it has its own. Initially it was cylinder, but it has been cut off just to examine this. And this is the cross hatch pattern, as I mentioned earlier, that while you are rotating you get the cross hatch pattern. So these are the cross hatch pattern. This is the finished surface 3D plot taken for this particular surface, and you can clearly see the difference between this and this surface. AFM image is showing surface texture, and this is the 2D plot, and this surface roughness from 339 nanometer has come down to 16 nanometer. So it clearly indicates the capabilities of our MREF process as far as surface finish and surface texture are concerned. Magnetorheological abrasive honing process, the same principle has been applied for the honing purposes, and this setup was designed and developed at IIT Kanpur. Now this setup was used for honing purposes by our MTech students, right. So these are the different parts, bottom cylinder, top cylinder. Here you will place the component for honing purposes, you will give the rotation. Here is the motor, pulley is there, and belt is also there. So it is rotational motion will be given so that you get the honing effect. Improvement in surface roughness and out of roundness profile by RMRF for cylindrical workpieces. Again 339 nanometer, 16 nanometer out of roundness. You can see here initial out of roundness profile, and this is something like this shown over here, and this is the final surface roughness out of roundness profile. As you can see clearly the difference between the two. Out of roundness is 6.49 micrometer, earlier 7.39 micrometer. It has reduced to some extent. We did not try too much, but we just wanted to see what is the difference between the out of roundness, initial out of roundness, final out of roundness. However, if you do it for sufficient time and optimize the parameter, you can improve the out of roundness of the finished component also. Internally finished cylindrical stainless steel workpiece. Now this is the another process which I am going to discuss, that is the magnetic float polishing process. Magnetic float polishing, MFP, use of magnetic field to support slurries in finishing ceramic balls and bearings. See, there are many processes which are available for finishing purposes, for flat workpieces, cylindrical workpieces, complex shaped workpieces, free form surfaces, but very few are available, or rarely one or two are available for finishing spherical balls or bearing balls. So this process, magnetic float polishing, needs lot of work to be done for this purpose, and these balls are used for bearing purposes also. Ferrohydrodynamic behavior of the magnetic fluid levitates balls abrasive particles and a float pad. We will see it. Levitation force is proportional to the field gradient, magnetic field gradient. You can see here, this is the magnetic fluid and abrasive grains. These are represented here. Magnetic fluid consisting abrasive particles. Ceramic balls are there which are to be finished, and these are the set of or bank of permanent magnet, north, south and so on, and you have the guide ring over here, and this is the drive shaft. You are rotating this drive shaft and moving slightly down to impose the force or the pressure, definite pressure on these balls, and they are supported by the float over here. And when you are rotating in initial pressure, after applying the initial pressure downward, these balls get finished to a very low surface roughness value, and this finishing rather improves, does not deteriorate the out of roundness of these balls also. Key features: finishing forces controlled externally by controlling magnetizing current. Here we are using the permanent magnet, but you can use the electromagnet, and if you are using the electromagnet, then you can control externally the magnetizing current, and then you can control the magnetic field, which is controlling the forces acting on these balls through these roller and through these abrasive particles over here and magnetic particles over there itself. Finish brittle silicon nitride balls and rollers up to 4 nanometer RA value, which is a very good surface finish. Limitations are there. Shape limitations is there. Spherical and cylindrical external surfaces only can be finished by magnetic float polishing process, and size limitation is also there, which will be governed by this as well as this gap over here. Magnetic float polishing, you can see here the forces when this is the balls to be finished, and here is the cylinder that we have already seen in the earlier sketch or earlier slide, and the forces are acting. This is the float which is supporting this, and here you have the fluid which consists of abrasive particles and the liquid, right, and this is finishing this surface. So different force analysis is there. Now you can see here out of roundness control is there. This is the initial roundness 22.5 micrometer, and finally it comes out to be 0.6 micrometer. So that is what I told you in the earlier slide, that you can improve the out of roundness rather than deterioration. So it clearly indicates that proper uniform finishing is taking place as proper uniform forces are acting on the balls. There is another process known as chemomechanical polishing. Let us take another process, chemomechanical polishing, CMP. It is very commonly used in electronic industries. CMP. Final removal is by mechanical wear, and isotropic removal selected contact among protruded area. We will see all this. Now you can see here, this is the workpiece. This is the, because here chemical is being used, so it reacts with the top surface of the workpiece, and this is the chemically reacted layer, and this layer is being removed, and this is the minimal amount of removal of the material. This is the nano size abrasive particle. So once you are removing this, so you are really indirectly removing the peaks and valleys on the top surface of the workpiece, and you get very good surface finish. As I mentioned, it is very commonly used in electronic industry. This the chemical etching takes place over here as shown over there, and peaks and valleys are there. So you are, while you are moving this, certain part of this top surface is removed, and it includes both peaks and valleys, and they are taken away, and whatever scratching or indentation is being done by this nano size abrasive particle, they will be remaining over here. So definitely the surface roughness will be in nanometer, or even in some cases you can get sub nanometer surface roughness values also. Now here what you are doing, let us see it. You have the slurry which is having the abrasive particle and the liquid, and here is the pad which is very soft, and this is the wafer face. This is the wafer at the bottom, here is the wafer. Now, so you are applying little bit of downward force, and this is the wafer carrier. So it is rotating, as you can see arrows given over here in this direction, downward force is being applied, pad is there, pad is rotating in this direction. So you can have, both are rotating in the same direction, but you, to increase the relative velocity, you can have in reverse direction also, but normally it is not done, because here final surface finish is more important than really MRR. It mainly includes the following two dynamic processes. The active component of polishing slurry reacts with the atoms of silicon, as we have seen in there, and the process is chemical reaction step. Second step is the process of desorption. The resultant reactants gradually separate from the surface of silicon wafer, and new silicon surface is exposed to polishing slurry. As we can see here quickly, that once this surface is removed, reacted surface is removed by this abrasive particle, then you get the new surface of the workpiece. Removal of silicon during CMP is explained by an attack of OH to silicon atoms, catalyzing the corrosive reaction of H2O, resulting in cleavage of silicon bonds. The chemical equation is as follows: Si silicon plus 2OH plus H2O, you get silicon oxide, silicate, and 2H2, that is the hydrogen gas. Now you can see here, interesting figure, hydrodynamic contact is there. Here are the you can wafer which is to be finished, it is held by the carrier, wafer carrier. Slurry is there in between the two, that we have seen in the earlier slide, and in the slurry you have the, this is the pad, and here abrasive particles are, iron particles are there, and you can clearly see the pad surface is there, and sorry, iron part, no, not iron particle, abrasive particles are there, and you can see the chemical here, large down pressure, small relative velocity is there because it is rotating with respect to each other, and this is the solid contact mode. Here no direct contact between the pad and the wafer is there, pad and wafer is there, but here you can clearly see the solid contact between the two, and these abrasive particles are removing the peaks or that reacted layer of the silicon, and that is separated out, so you get the fresh surface of the workpiece. Now we have many limitations of the processes that we have already discussed. Just now we discussed the chemo-mechanical polishing, earlier we discussed the MRAF process, and before that we also discussed abrasive flow finishing process. Now all the three have their own limitations. So what we did at IIT, it should be plus rather than equal to. What we have done at IIT Kanpur is that we combined all these processes and developed a very new process, chemo-mechanical magnetorheological abrasive flow finishing process. This work was done by Dr. Prabha, who is working at Bark Bhava Atomic Research Center, Bombay, Mumbai. Very interesting and very good process. Limitations of CMP that we have just seen, CMP process, it is not able to do planarization with constant finishing throughout the work surface except circular work surface. So for circular work surfaces it is good comparatively, but not for all kind of the surfaces it is not good. It does not have flexibility regarding work surface, shape and size, because flat surfaces are fine. If surfaces are curved, they are 3D, it cannot work properly. So what is done? Chemo-mechanical polishing and magnetorheological finishing, they are combined, along with abrasive flow finishing characteristics are also taken into consideration. So you can call it chemo-mechanical magnetorheological abrasive flow finishing, or the person who worked on it, he likes to call it as chemo-mechanical magnetorheological finishing process, that is CMMRF process. Magnetic field assisted polishing pad instead of conventional polishing pad of CMP is used in this particular case. Flexible polishing pad removes shape limitation on workpiece surface. Here he is using the flexible polishing pad. Mechanism of finishing continued. The main use of MRP fluid, magnetorheological polishing fluid, is to chemical reaction with the silicon substrate to soften it. Chemicals in the MR fluid react with surface materials, form the chemical compound, because we have seen already in CMP, there is the chemical reaction. It forms the chemical compounds that can be removed by abrasive as well as magnetic particles. They are there in fluid, polishing fluid. In aqueous solution, oxide forms hydroxyls. They should be easily removed by magnetic or abrasive particles. CeO2 becomes chemically active and soft abrasive to silicon substrate. It is used for ultra finishing. You can see very interesting picture. You can see here, these are the CIP, carbonyl iron particles. This is the abrasive particles, and you are applying the downward force for its penetration into the surface, and this axial force for moving it in this direction, and this abrasive particle over here, it will shear off the surface over here. This is the abrasive particle. When it moves in this direction, it will shear off the peak and surface roughness value is decreased. If you see this figure, this top surface has been removed in the form of the chip, as you can see over here. This is written as chip over here, and this is separated out. So you have the micro nano chips, and this is how it is removing it mechanically. Silicon workpiece is there, chemical reaction is taking place. So whatever layer is being formed, this silicon layer, it is being removed by the abrasive particle, the way it is removing here. This whatever layer is formed, that also has peaks and valleys, and it is sheared off. Chemical reaction zone. Now here it is written soft abrasive, because this very hard layer after chemical reaction has become soft. So you can use the softer abrasive particles rather than very hard abrasive particle for finishing very hard materials. Formation of flexible polishing pad. You can see here magnets are there, cover plate is there, and here you can see abrasive particles are there, iron magnetic particles or iron particles are there. All these abrasive iron particles will get attracted towards the magnet. So you can see all of them are near the magnet, while abrasive particles being non-magnetic, they are on the outer periphery, and this is the outer periphery in which contact the workpiece surface will come. So really speaking, the workpiece material from the workpiece will be removed by these abrasive particles, and this is the MR fluid under a specified working gap over there. Abrasive particle is there, and this is the base material. MRP fluid without any magnetic field, all are distributed randomly. There is no magnetic field over here. MRP fluid under magnetic field, you can see here, they get aligned. North and south pole is there. CMMRF system, nano finishing system. It was developed by BARC and IIT K jointly, and major components of the systems include finishing tank, precision orientation table, polishing head with rotary spindle, CNC programmable XY stages, CNC controller for finishing head movement, slurry system for chemical as well as magnetorheological polishing fluid, slurry circulation system, controller and monitoring of slurry parameters. This is very important. If you can online control the slurry parameters, you can control the finishing process, and that is the main advantage of this particular process, that you can externally control the finishing process by controlling the finishing parameters. And this is the setup which was developed by Prabhat Ranjan. You can see over here various parts are there. These are the panel shown over here, and this has been developed at Bark by Prabhat Ranjan while doing his PhD. You can see some part, VFD for spindle variable feed drive, VFD for workpiece feed, this is for spindle rotation, this is for the workpiece, dial gauge to control working gap, to monitor and control the working gap, that is used over there. Now spindle is here, all parts are shown over there. This is the workpiece is here, this is the MR polishing fluid, and when you are rotating this, MR polishing fluid also rotates over there, and here is the fixture, you have the North Pole. Now this is the magnetically stiffened MR polishing fluid, you can see here, this has been stiffened, and this is the compacted MR polishing fluid. When finishing is taking place, it is compacted and it is spread, this part gets spreaded over there on the workpiece surface depending upon what shape and size of the top pad or plate is there. Here are some experimental results. This is the initial surface, see it carefully how it is changing, initial surface, and then you have the intermediate surface here, polished with silicon carbide 800 oil based MRP fluid, and this is what from here you get this particular surface, and polished with silicon carbide 400 oil based MRP fluid, this is what you are going to get. But here and here comparison is there when you are using different size of the polishing this MRP fluid, this silicon carbide abrasive particle, different shape is there, but still you can see here scratches are there on the finished surface. These are the scratches, you can clearly see them over here, over here, over here. So various many scratches are shown over there on the finished surface. Now polished with water based MRP fluid, so you can clearly see the advantage of using water based MRP fluid compared to the oil based MRP fluid. And you can see this 2D plots of surface roughness. You have, please note it carefully, 1210 nanometer, that is 1.210 micrometer surface roughness value initially, and this is the 2D plot. And after finishing over here you have 0.10 nanometer surface roughness, that is 10 angstrom, and you can see the drastic change in the surface roughness value. Now best surface finish obtained on silicon is, sorry, let me just go back for a minute. If I remember correctly, it should be around 10 nanometer rather than 0.10 nanometer. So you can see here it has reduced from 1210 to 10 nanometer, that is more than 121 times reduction is there. Now the best surface finish obtained by him was 0.5 nanometer on silicon substrate, which is nothing but, actually it was 4.85 angstrom, that is approximately 0.5 nanometer, and you can compare it with the size of the atoms. So this is the initial surface roughness, rough surface, and then it was finished to 0.5 nanometer, and you can clearly see this is the finished surface, and you can clearly see the reflection of IIT K and bark over here. This is the finished surface. This is the another finished surface where you can see the reflection of IIT K, bark and DST. And please note it, this surface roughness value, best surface roughness value was 4.85 angstrom, that is 0.485 nanometer. Optical views of finished surface. You can see here again reflection. This is the image of finished surface under sunlight. This is the another one. It is reflecting image of books. This is the book over there, so its reflection are there. Finished silicon substrate with brass, and another view of the finished component. Results. Initial surface roughness values are 1.21 micrometer and so on. This is another one. This is the finished one, semi-finished rather, and this is the fully finished surface. So you have 0.5 nanometer, which was claimed in the earlier slide. This is the 0.5 nanometer surface, that is exactly 4.8 angstrom, approximately 0.5 nanometer. So you can clearly see the difference. We started with 13.4 nanometer over here and ended up with 0.5 nanometer over here, that is approximately 5 angstrom. Now, after achieving such a good surface finish in terms of angstrom, the question that we raised is what next? We can use it for optical design for optical components. You can use these processes for finishing purposes, especially ISRO Ahmedabad is using some of these processes for finishing purposes, especially the mirrors that require nano finish over here. They can be finished to the nano level or even sub nano level, as we have already shown you one component on the silicon. Nano finishing of mirrors at RR-CAT Indore, they are also using such kind of the devices for space research purposes. Now, front view of hip joint, because these are the human body implants, they are very important, and they should be finished so that patient do not feel any pain after putting those implants. So, hip joint, some work has already been done at IIT Kanpur regarding finishing of hip joint. This is the front view of pelvic bone, and this is the joint capsule, this one. And in another lecture, I have shown you how it is finished by other processes. Then you can see over here, this is the kind of the thing which is being ring prosthesis. This is the ring prosthesis. So all these implants, they can be very efficiently finished, can be finished easily up to nano level or even sub nano level. And this is very important for the life of the implant as well as for the comfort of the patient. Now, at IIT Kanpur, one of the master's student of dental surgery, she finished the crown finishing setup was developed at IIT K. This is the one which was developed over there, and this was finished with the MRF process. This is the brush for finishing those dental crown. And you can see here one spot just for taking the picture. It was finished spot in artificial crown after polishing. So very good surface finish was obtained, and this finish will help in many ways to the person who is using these artificial implants or artificial crown, because if rough it is, then it will create various kinds of the problem. So finishing of these crowns, artificial crown, is very important. Now this is the another human implant which is being finished. You have the nano-finishing of human implants over here also. Conclusion: based on the nano-finishing techniques discussed here, it is concluded that simple and complicated components can be finished to nano level surface roughness value by using an appropriate finishing method. I have discussed many finishing methods being used across the globe. So you have to very carefully choose a proper finishing method. There is a need of serious dialogue between the researchers working in the field of nano finishing technologies, end users, public and private sector both, and government, so that in-house developed technologies can be more effectively used for the benefit of the nation. There is enough scope for the utilization of the in-house developed nano finishing technologies in the strategic areas such as defense, aerospace, nuclear power plants, automobiles, biomedical implants, etc. There is a need for the young scientists, engineers to come forward and interact with the end users and to work in these kinds of highly interdisciplinary areas. More than that, when we want to finish the biomedical implants, I personally feel there should be the joint efforts made by the doctors and the engineers, so that they can make the best use of engineering technologies available for enhancing the performance of biomedical implants. Thank you very much.